All right. So lesson 20.7, which is the ratio test. The only theorem that we have here. Actually, this, I think, is kind of one of the easier tests to do. It's just a bunch of algebraic simplifying, and then you take a limit. And the limit is as n goes to infinity. So finding limits as n goes to infinity, we've been working with those a long time, and they're pretty easy to do. So what this theorem says is if you have a series of positive terms. So again, we're looking at positive terms only. Pretty much everything that we've talked about so far has been only positive terms. Okay, all of the big theorems, the new theorems that we've learned. If you take this series and you look at the u sub n term of the series and you calculate the ratio of the n plus 1th term to the nth term, so u sub n plus 1 to u sub n, and you simplify that and you find the limit as n goes to infinity. Based on that value, which we're going to call r, that will tell you whether or not you can determine if the series converges, diverges, or if you can't tell anything, nothing is shown, which means this test fails. So if the limit as n goes to infinity of that ratio of the n plus 1 term to the nth term is less than 1, then our series is convergent. If the ratio, or the limit of the ratio, is greater than 1, then the series is divergent. If it's equal to 1, nothing is shown and the ratio test fails. And that's it. That's all we're going to do. So, question number 1. We're going to investigate this by using the ratio test. So we're going to look at our u sub n term. So we see here we have our u sub n term. There's our u sub n term. And we're going to calculate u sub n plus 1 divided by u sub n. And then we're going to find the limit as n goes to infinity. Quick second. There we go. Oh, I can't do that. Oh, maybe I don't know. Okay, so we're going to calculate this as n goes to infinity. So first, let's just calculate the ratio. If you want, you can calculate the ratio separate, and then you can put the limit on it so that you don't have to write limit on every single line. And so I'm just going to calculate u sub n plus 1 divided by u sub n. And so calculating my u sub n plus 1, I'm just plugging in n plus 1 for all of the n's. And then I'm going to simplify. So just go ahead and do that. So we have in our numerator n plus 1 over n plus 1 plus 1. And you can simplify this a little bit as you're plugging it in. I'm just going to write it out completely by just plugging in n plus 1 first and then simplifying. And then multiplied by 1 over 2 to the n plus 1 minus 1. All over u sub n over the quantity of n plus 1 multiplied by 1 over 2 to the n minus 1. And so now I'm going to simplify numerator and denominator. And I have a fraction and a fraction, so I'm going to take my numerator and then I'm going to multiply by the reciprocal of the denominator right away so that I can cancel things out. So then my numerator, I'm going to have n plus 1 over n plus 2 from that multiplied by 1 over 2 to the n. And then I'm going to multiply that by the reciprocal of the denominator. So my denominator's reciprocal is going to be n plus 1 over n times 2 to the n, and 2 to the n minus 1. I'm going to write it as 2 to the n times 2 to the negative 1 over 2. Because then I can cancel the 2 to the n with the 2 to the n. All right. Oh, I'm sorry. Yes, thank you. Get rid of that. That should be a 1. Cool. All right. So now I have my u sub n plus 1 divided by u sub n. So we have n plus 1 quantity squared all over that 2 to the negative 1 is going to go down to the denominator. So 2n times the quantity of n plus 2. And now I need to take the limit as n approaches infinity. So over on the right here, I'm going to do limit as n approaches infinity of the u sub n plus 1 over u sub n. Let me just write that in here. I'm going to expand that as I fill this in. So n plus 1 quantity squared is going to be my n squared plus 2n plus 1 all over 2n squared plus 4n. And since we're doing a limit as n goes to infinity, we're going to divide by the greatest power of the denominator. Don't forget to do the denominator. Don't do the greatest power of the numerator. In this case, it's the same. However, I saw some people on their test divided by the greatest power of the numerator instead of denominator. So we're dividing everything by n squared, so we get 1 plus 2 over n plus 1 over n squared all over 2 plus 4 over n. And looking at that goes to 0, that goes to 0, this goes to 0, and so we get that the limit is equal to 1/2. Since the limit is equal to 1/2, that falls in the classification of r is less than 1. So we can write since, actually I'm going to define this here as r. Since r is less than 1, the series converges by the ratio test. And there we have it. So we can start by calculating our u sub n plus 1 divided by u sub n. So u sub n plus 1 divided by u sub n. So we're going to get 2 times the quantity of n plus 1 minus 1 quantity factorial over 5 to the 2 quantity n plus 1 minus 1. Just write that a little bit better. I wrote that kind of big. That's your u sub n plus 1. Dividing that by the u sub n. So quantity of 2n minus 1 factorial all over 5 to the 2n minus 1. So simplifying, I'm going to go ahead and multiply by the reciprocal right away. So in the numerator, we end up with 2n plus 2 minus 1. So 2n plus 1 quantity factorial divided by the denominator 5 to the 2n plus 2 minus 1. So 5 to the 2n plus 1. And then I'm going to multiply by the reciprocal of the denominator. So that's 5 to the 2n minus 1 all over quantity of 2n minus 1 factorial. So with the factorials, you can expand and expand one out until it cancels with the other. So which one's bigger, the 2n plus 1 factorial or 2n minus 1 factorial? Okay, so we're going to expand 2n plus 1 factorial. So 2n plus 1, what do I multiply by next? Next. Cool, so now that matches the denominator, so I'm going to put the factorial on that. And then my powers, I'm going to write those out. So that's 5 to the 2n times 5 to the negative 1 all over 5 to the 2n times 5 to the positive 1 multiplied by quantity of 2n minus 1 factorial. So our 2n minus 1 factorials will cancel. Our 5 to the 2n's will cancel. My 5 to the negative 1 then can move into my denominator. And if I expand out my numerators, then I'm going to have 4n squared plus 2n. That 5 to the negative 1 moves into the denominator to give me 5 times 5, so 25. Yes? Oh, you're not raising your hand? Cool. All right, and now we're going to calculate the limit. So r is equal to the limit as n approaches infinity of the u sub n plus 1 divided by u sub n. So we have the limit as n approaches infinity of what we just calculated, 4n squared plus 2n all over 25. Since there's no variables in our denominator, then this limit is going to go to infinity. So infinity does not exist, but infinity is what we're going to look at. Is infinity greater than, less than, or equal to 1? Greater than 1. So, since r is greater than 1, the series diverges by the ratio test. Okay, so on number 3, it's actually expanded out already, so you can see the nth term and the n plus 1th term. And so we can use this here is our u sub n, and then this here will be our u sub n plus 1. And you could use the 1 over n plus 1 quantity squared as your u sub n, and then your u sub n plus 1 would just be 1 over n plus 2 quantity squared. That would also work. But those two terms match, and then the first one you can use as your u sub n, the second one you can use as your u sub n plus 1. So we're calculating first our ratio, u sub n plus 1 divided by u sub n. So 1 over the quantity of n plus 1 squared, all over 1 over n squared. Multiplying by the reciprocal, I end up with n squared over, I'm going to expand the n plus 1 quantity squared, n squared plus 2n plus 1. And then I'm going to find my limit. So r equals the limit as n goes to infinity of n squared over n squared plus 2n plus 1. What's this limit going to equal? 1. So what is that going to tell us? Nothing. So we have 1 over dividing everything by the greatest power of the denominator to show all of our work, plus 2 over n plus 1 over n squared, showing that the parts go to 0. These two parts both go to 0. We end up with 1 over 1, which is 1. And the directions on this just said to investigate the ratio test. So all we're doing is doing the ratio test, seeing what we can figure out from the ratio test. Okay, so by the ratio test, this tells us nothing. So by the ratio test, nothing is shown. Since r is equal to 1. Or you can write r is equal to 1, therefore nothing is shown by the ratio test. So let me show number 4 and number 5. You guys see both of those on there. So there's number 4 and number 5. Try number 4 and number 5 on your own. So here's the work for number 4. Everybody said that they got 4/3. Actually, you got that as the constant, and the limit of the constant was a constant, which means it diverges by the ratio test. Everybody good with that one? Okay. And then when you did question number 5. So after plugging that in, simplifying and calculating, you ended up with n squared plus 1 over n squared plus 2n plus 2. Everybody good with that? Is that what you guys got? And then when you found the limit of that, and you did, okay, well now r is the limit as n goes to infinity of that, you ended up with that limit was equal to 1. Therefore, the ratio test fails. So then what we're going to do is we're going to find another way to prove the convergence or divergence of this one. So we're going to extend this one a little bit further to prove the convergence or divergence. So at this point, you're running through all of the different things that you know, right? Is it arithmetic? Is it geometric? No, no. What if you find the limit of u sub n? The limit of u sub n in this case, you can just do that in your head. What's the limit of u sub n going to equal? So what does that tell us? Darn. So then you have to find something else. Anybody have another idea of another test we could use? All right, so we're going to use comparison test. And so on your paper, you can label it comparison test. So you can just use CT so that we know we're doing comparison test. And then our hypothesis, you said you wanted to compare to 1 over n squared, which was a known convergent series. So comparing it to 1 over n squared, if we want to prove convergent, we're going to ask ourselves, is our u sub n term, u sub n again is just 1 over n squared plus 1. For convergent, are we going to do greater than equal to or less than equal to? All right, less than or equal to 1 over n squared. So we're trying to figure out if that's true, so I multiply both sides by n squared. I multiply both sides by n squared plus 1. I can subtract n squared on both sides. 0 is less than or equal to 1. Is that true? Awesome. And so then I can state my conclusion by the comparison test. So I write out my sentence just like we did with comparison test. The given series is convergent. Oh, not yet. The given series is less than the known convergent P series P equal to 2. Therefore, the series also converges.